let's consider the same situation with F equal 5 and K equal 2, representing 5 Newton constant force and a drag force that's determined by the constant 2 newtons per meter per second, 2 Newton seconds per meter, and now a mass of 4, which might correspond to 4 kilograms. Again, if you don't know the physics, don't worry about the units. The idea is going to be fairly clear, I believe. And V naught equals 8, which would stand for 8 meters per second. Now the graph of V versus T, and let's call this V and let's call this T. We're going to again have terminal velocity 5 halves, but now we're starting at a velocity that's greater than 5 halves, so that we are going to we're going to expect the velocity to decrease toward 5 halves. And of course the reason physically that the velocity decreases is that this drag force minus kV is bigger than the force F that's pushing the object forward, so that the object is going to be pushed in the backward direction, meaning that it will slow. So we expect a solution of this nature. Now, our solution, of course, is of the form F over K plus C e to the negative K over mt, this form, with C, as we've seen, equal to V naught minus F over K, so that our C is 8 minus 5 halves, which is 11 halves. And that simply corresponds to how far the initial velocity is above our terminal velocity. That's how much difference we have between how fast we're moving and how fast this thing will be moving if it's in equilibrium. With this value of t, our solution becomes 5 halves plus 11 halves e to the negative 2/4 t. And all we're doing is we're substituting. We've got the 5 halves for the F over m. The c, as we've seen, is 11 halves. And it's e to the negative k over mt with k equal to 2 and m equal to 4. Solution comes out 5 halves plus 11 halves e to the negative t over 2. If t is equal to 0, then e to the negative t over 2 is 0, and we just have 5 halves plus, did I say e to the negative t over 2 is 0? E to the negative, if t is 0, e to the negative t over 2 is e to the 0, which is 1, leaving us just the 11 halves, which we add to the 5 halves, and that does give us our initial velocity of 8. So t equals 0, the velocity is what it should be. As t approaches infinity, let's see if I can say this right for a change, e to the negative t over 2 becomes e to a negative large power, which is 1 over e to a positive large power, which is 1 over a very large number, which approaches 0. So that this number, fairly rapidly in fact, approaches 0, and this whole term goes away, leaving us a velocity of 5 halves, so that as t becomes large, we approach the expected terminal velocity of 5 halves. And this is all consistent with the picture. If we draw a slightly larger representation of our graph, okay, here we are at our terminal velocity of 5 halves. Here's our initial velocity, 8. Here is our function, 5 halves plus 11 halves e to the negative t over 2. If we were to draw a graph of the function, 11 halves e to the negative t over 2, halves might be here, and our function would start with value 11 halves at t equals 0 and approach horizontal asymptote along the t-axis. So this would be the function 11 halves e to the negative t over 2. What do we do to that function? We raise it 5 halves of a unit by adding 5 halves, and we get this function. So we take this function, raise 5 halves in the y direction, and we get this function, where the function 11 halves e to the negative t over 2 is sitting here right on top of the horizontal line, y equals 5/2, representing a situation where we start at a speed or a velocity 11/2 greater than the terminal velocity and approach the terminal velocity along this curve, giving us a y versus t curve that approaches the terminal velocity 5/2 along an identical curve.